I will now continue looking at saturated neurons and vanishing gradients. In the last video, I discussed 3 mitigation techniques for saturated neurons and vanishing gradients. I will now look at 2 more techniques. I will start with the cross-entropy loss function. Let's now look at the output layer in detail. If we are not careful, we can get these neurons to enter the saturation region. Let's assume that we are working with a sigmoid neuron. We are building a classifier. That is, we are training this output neuron to output either 0 or 1. For example, I want to classify an email if it is spam or not spam. That is, we are training this neuron to enter the saturation region. To gain some insights here, we need to look at the interaction between the output neuron loss function and the backpropagation algorithm. The backward pass starts with the derivative of the loss function. If we use the mean squared error loss function, the derivative is the negative difference between the truth and the output. Y hat represents the output of the network, and Y is the ground truth, our data that we know that is true. Then we compute the derivative of the logistic sigmoid function, which is the S times minus S. S times 1 minus S. Then we multiply both of these together. Now let's look at the details by plotting these values for different result values. This chart shows 3 curves. The blue one is the derivative of the mean squared error loss function. The orange one is the derivative of the sigmoid activation function, and the green is the product of these 2 derivatives. The chart visualizes the change of these values based on how far the network's output is from the desired output. We assume that the desired output is 0 for this example. That is, on the left side, the network output matches the ground truth, and the neuron is in one of its saturation region. On the right side, the network output is 1.0, this one, which is opposite of the ground truth, the opposite of the desired value, and the neuron is in the another its saturation region. Now, let's look at the 3 curves between these 2 points. So we start with the blue curve, which is the derivative of the mean squared error loss function. On the left end here of the chart, this derivative is 0. We start backpropagation with a derivative of the mean squared error loss function. In this case, we will inject 0 backwards to the network, which will not adjust anyways. However, that is not a problem, given that the output is already producing the desired value. Moving to the right end of the chart, we see this derivative is 1.0. We will inject this non-zero or this 1.0 value in backward to the network in the backpropagation algorithm. And there is video that I discussed the backpropagation algorithm in details. This will potentially adjust the weights to get the desired behavior, so everything seems good at this point. Now let's look at the orange curve, which is the derivative of the sigmoid function. On the left side, this derivative is 0. That is not a problem. As we move to the right, the derivative increases as the output diverges from the desired value. However, when we then go to the very far right here, we see that this derivative approaches 0. Let's now see how this affects the green curve, which is the error term for the output neuron. We get the green curve by multiplying the derivative of the loss function and with the activation function. So the blue curve multiply with the orange curve. We get the green curve, which is the error. We see that moderately far from the desired value, we have a non-zero error term. This will propagate backward and can adjust the weights. However, if the output is close to 1.0, which is opposite of the desired value, we see that this green curve, which is the error term for the output neuron, is 0. No error will propagate backwards and no weights will be adjusted. The network will not learn. This is a big problem, and a solution to this to consider using a different loss function. We will explore that on the next cell. Here, on this cell, we will introduce the cross-entropy loss function that can be used instead of the mean squared error. This is the formula shown here. The chart shows how the derivative of the cross-entropy loss function behaves as a function of the network output. We saw in the previous slide that for the derivative of mean square error, it approached 1.0 as the output approaches 1.0. The derivative of the cross-entropy loss function will approach infinity as the output approaches 1.0. We see that from the blue curve moving steeply and going outside the chart as we go and move to the right. Let's see how this affects the green curve. We know that as we approach 1.0, the sigmoid neuron derivative will approach 0. That is the orange curve. When we now multiply that by the derivative of the cross-entropy loss function, which approaches infinity, the product will approach 1.0. That is, if the output neuron is the opposite to the desired value, we will still have a non-zero error for the output neuron. And this will enable us to adjust the weights and to let the network to continue to learn. The chart compares the two loss functions, and we can see they are actually not all that different. We see how the loss functions changes as the network output is moving further away from the desired output of 0. At the left side of the chart, where the network output matches the desired output, both loss functions are zeros. As the network output moves further away from the desired value, both loss functions increase. The only difference is that the cross-entropy loss function increases faster than the mean squared error loss function. And we saw in previous slide that this will counteract the problem with a saturated output neuron. Therefore, the cross-entropy loss function is a better choice to use when you use a sigmoid neurons in the output layer. Let's see how we can program this cross-entropy loss function. Looking at the function, we see that it consists of two terms. The first term has y as the factor, and the second term has y minus y as its first factor. Y is the desired output of the network, which is either 0 or 1. This means that in all cases, either y or 1 minus y will be 0. In other words, y and 1 minus y will act as if statement. It will select either the term negative len y hat or the term len 1 minus y hat. This typical code implementation is shown here on the cell. This was a lot of information about the cross-entropy loss function. However, as a deep learning practitioner, the only thing you need to remember to use the cross-entropy loss function when you use a sigmoid neuron for your output layer for the classification task. The deep learning framework like TensorFlow or PyTorch will handle the details for you. So we looked at the number of techniques to avoid saturation, and we work with sigmoid and tanh neurons. Another alternative is to use a different activation function that avoids saturation altogether. Starting at the upper left, we see our tanh function that we have looked at in detail. We see the slope approach 0 on both ends. The other charts on this slide show alternative activation functions. Now we'll talk about the restified linear unit, also known as the ReLU neuron. We can see that it saturates on one side, but on the other, it isn't saturated. If we compare it to the tanh and sigmoid neurons, we see that it's somewhat different. The sigmoid and the tanh with smooth functions and had its derivative defined in all points. ReLU has a kink in the curve, which means that technically its derivative is undefined in one point. But in practice, this is not a problem. We can define the derivative as 0 in that point. The key thing here is to avoid curves that has discontinuities. The benefit with the ReLU function is that it's very simple to compute. You can start with it. If the weighted sum is negative, the output is 0. If the weighted sum is positive, the output equals the weighted sum. Now let's talk about another activation function, which is leaky ReLU activation function. This addresses the issue that the ReLU function is saturated in one of the sites. Now we have soft plus function. It's similar to ReLU neuron, but it's smooth rather than having a kink in the curve. We have also exponential linear unit, or you can call it LU unit. This is similar to leaky ReLU, but it's again smooth rather than having the kink in the curve. Finally, we have max out function. This is a generalization to the ReLU function, but it has multiple line segments. In this example, we have 3 segments, but you can increase these segments if needed. The question is, which activation function should we pick? Actually, this is a design choice that you will have to experiment with. As a rule of thumb, you can start with ReLU unit because it's so simple, and then check the behavior with that and compare it to the behavior with other functions and settle on something that works for your use case. Now I will summarize the techniques. So you will want to normalize the output. This will keep the weighted sum small to reduce the risk for saturated neurons in the input layer. Also, you can apply batch normalization, which reduces risk of saturated neurons in the hidden layers. You should pick a suitable weight initialization scheme. This will keep initial weighted sums small. If you use a sigmoid neuron in the output layer, you should use the cross-entropy loss function. This will ensure that the gradient will propagate even if you have a saturated output neuron. And finally, you can choose to use a different activation function to avoid the saturation problem altogether.